us start numericals on this topic. Applicable formulae. Number 1, Kc equal to active mass of C raised to small c, active mass of D raised to small d, active mass of A raised to small a, active mass of B raised to small b. As you know, where C and D are the product and while A and B are the reactant for the given reaction. Applicable formula number 2, Kp equal to P, that is a concentration in terms of gaseous species, into C raised to C into P D raised to small d, whole upon P capital A raised to A P capital B raised to small b. Applicable formula number 3, Kp equal to Kc into RT whole raised to delta N. As you know, where delta N is a change in number of gaseous moles. These are the 3 applicable formulae while solving the numericals. Right? Let us start then numerical number 1. Before putting the numerical number 1, I will repeat these 3 formulae. Number 1, Kc equal to active mass of C raised to C, active mass of D raised to small d, whole upon active mass of A raised to A, active mass of B raised to small b. Kp equal to P C raised to C into P capital D raised to D, P capital A raised to A, P capital B raised to B. And third formula, Kp equal to Kc RT whole raised to delta N. Now numerical number 1. I will write first numerical. In a reaction vessel, of 1 dm cube volume, hydrogen gas react with iodine gas to form hydrogen iodide. Hydrogen iodide gas at 300 Kelvin at equilibrium, 2.5 moles of hydrogen 6 moles of iodine and 25 moles of HI, hydrogen iodide, were found. Calculate equilibrium constant for the given reaction at the given temperature. At the given temperature. This is the numerical number 1. In a reaction vessel of 1 dm cube of volume. Volume is given 1 dm cube. Hydrogen gas react with iodine gas. These are the two reactants, hydrogen and iodine, to form hydrogen iodide. Means product is hydrogen iodide. Then at equilibrium, reaction occurs, equilibrium established, and at equilibrium 2.5 moles of hydrogen, 6 moles of iodine and 25 moles of hydrogen iodide were found, and we have to calculate equilibrium constant. Equilibrium constant. Now, first of all, we have to write chemical reaction from the given information. Chemical reaction is H2 plus I2 gives 2 times CHI. This is the given reaction from the given numerical, right? Then these are the 3 points. Point number 1, initial moles are directly, initial moles are not given, directly moles at equilibrium. Moles at equilibrium. H2, how many moles at equilibrium are given in the given numerical? 2.5. Therefore, below H2 we have to write 2.5. Below I2 we have to write 6 moles. And at equilibrium, how many moles of HI are formed? 25. 25. Second point, concentration at equilibrium in moles per dm cube, because concentration is expressed in moles per dm cube. Now, moles are 2.5 at equilibrium and volume is given 1. 6 moles of I2 are given, volume is 1. 25 moles, volume is 1. Means given moles divided by volume is nothing but concentration. Already we explained meaning of concentration. Concentration is nothing but number of moles per unit volume. Here number of moles are 2.5, volume is 1, therefore 2.5 divided by 1 is nothing but concentration of H2 at equilibrium. Similarly, 6 moles of I2 divided by 1 volume, means 6 by 1 is nothing but the concentration in terms of moles per dm cube at equilibrium. Similarly, concentration of HI, 25 moles at equilibrium, volume is 1. Therefore, 25 divided by 1 is nothing but concentration of HI at equilibrium. Then apply the law of mass action to this reaction. After applying law of mass action, to above chemical reaction, we get Kc equal to equilibrium constant. Concentration of HI means active mass of HI raised to 2, number of moles of 2, therefore raised to 2, whole upon concentration of H2 into concentration of I2. Number of moles of each is 1, therefore raised to 1, and 1 is not, it is not necessary to write 1. Then we have the value of active mass, we have the value of molar concentration at equilibrium of HI. HI concentration 25 upon 1 whole raised to 2 upon concentration of H2 2.5 upon 1 concentration of I2 6 upon 1. Now simplify. Square of 25 is simple. Now if we write 25 into 25 upon 2.5 into 6. Simple, right? Now then divide it. If we write again, it's simplified. 25 into 25 upon 25 into 10 raised to minus 1. This point is deleted, and then 10 raised to minus 1 into 6. 25 get cancelled. Simple point, right? Then we will divide it 25 divided by 6 equal to 4 point divided by then 1 then left 4 then 6 divided by 10 raised to minus 1. Then it is equal to 10 raised to minus 1 shifted towards numerator, it becomes then 41.66. This is your final answer, and therefore equilibrium constant for the given reaction is 41.66. This is your final answer. It has no unit, right? Because moles per dm cube get cancelled. This is your final answer for the given numerical, right? I will repeat the same. One volume is 1 dm cube. Hydrogen gas react with iodine gas to form hydrogen iodide at 300 Kelvin. At equilibrium 2.5 moles. We have written 2.5 moles. 6 moles of iodine and 25 moles of HI were found. Therefore, we written a reaction. H2 react with I2 to form twice HI. 2 points are there. Then moles at equilibrium 2.5 H2, 6 I2, 25. Concentration at equilibrium in moles per dm cube. Moles per dm cube. Dm cube is 1. Therefore, 2.5 divided by 1. That is the concentration of H2 at equilibrium. 6 divided by 1, that is the concentration of I2 at equilibrium, and 25 divided by 1, that is the concentration of HI at equilibrium. Then we applied law of mass action to this chemical reaction, then we get Kc equal to active mass or molar concentration of Hi raised to 2 molar concentration of H2 into molar concentration of I2. Then we have the values of these concentration. These are the concentrations substituting, right? 25 1 raised to 2, 12.5 divided by 1, 6 divided by 1. Simplification then 25 into 25, 2.5 into 6. Remove this point and then multiply by 10 raised to minus 1. This therefore 25 get cancelled. 25 divided by 6 it becomes 4.166 divided by 10 raised to minus 1. It becomes in numerator plus, therefore it becomes 41.66. Therefore answer is Kc equal to 41.66. I hope you are getting me, right? This is the first numerical, right? Any doubt? Then we will start then second numerical. One mole, second numerical, 1 mole of SO3 sulfur trioxide was placed in a vessel of volume 2 dm cube at 450 degrees Celsius. Full stop. At the equilibrium, the vessel was found to contain vessel was found to contain 0.5 moles of SO3. Calculate equilibrium constant for the given reaction at the given temperature. At the given temperature. Now, this is the numerical number 2. Yes, concentrate uranium wood. 1 mole of SO3 was placed in a vessel of volume 2 dm cube at 450 degrees Celsius. At the equilibrium, the vessel was found to contain 0.5 moles of SO3. Calculate equilibrium constant for the given reaction. Right? Now, from the given reaction, we will write first chemical reaction. That is SO3 gives SO2 plus O2. Now to balance this reaction, twice SO3 and then twice O2. 2 into 3, 6 oxygen, 2 into 2, 4, and these are the 2 oxygen atoms, and 2 sulfur. Equation is balanced. This twice SO3 gives twice SO2 plus O2. This is the balanced chemical reaction for the given numerical. Then 1 mole of SO3 was placed in a vessel. Means initial mole is given. Therefore, here another one point, initial moles. How many moles of SO3 was placed in a vessel at initial stage? 1. At initial stage, no products are formed, therefore products are 0, 0. Products are 0, 0. Now second point, moles at equilibrium. Interesting point. Now concentration is important to receive this second point, moles at equilibrium. We started initial moles, right? Then our aim is to calculate moles at equilibrium. Yes, here at the equilibrium, the vessel was found to contain 0.5 moles. Directly 0.5 moles of SO3 are given. Then how many moles of SO2 are formed? Here ratio is 2:2. Therefore 0.5 to 0.5 same. Because whenever the 2 moles of SO3 get reacted, how many moles of SO2 are formed? 2. Then here, how many moles left of SO3? 0.5. Therefore, same 0.5, but here O2. Whenever the 2 moles of SO3 get reacted, how many moles of O2? 1. Means exactly half. Therefore, 0.5 moles left at equilibrium. Therefore, how many moles of O2? Exactly half. And half of 0.5, that is a 0.25. That is 0.25. Any doubt about this point? I'll repeat the same. Whenever the 2 moles of SO3 get react, 2 moles of SO2 form is same. Therefore, 0.5 moles left, 0.5 moles form same. But here, 2 moles of SO3 when reacted, 1 mole of O2 are formed. Exactly half O2 form. Therefore, 0.5 left, exactly half of that, 0.25. Right? Then third point, concentration in moles per dm cube at equilibrium. At equilibrium, concentration moles per dm cube at equilibrium. At equilibrium. Now, how many dm cube? 0.5. Therefore, 0.5 upon 2 dm cube. 0.5 divided by 2, 0.25 divided by 2. Therefore, it is nothing but half of this, 0.25. This is the concentration. Similarly, 0.25. This is the molar concentration of SO2 at equilibrium. Here, 0.125. This is the molar concentration of O2 at equilibrium. Then After applying law of mass action to this equation, we get after applying law of mass action to given chemical reaction, we get equilibrium constant equal to, now concentrate rather than this reaction, active mass of these two raised to their moles, active mass of this raised to this moles. Therefore, active mass of SO2 raised to 2, active mass of O2 upon active mass of SO3 raised to 2. Yes. Now we have the values of these concentrations. We know concentration of SO2 0.25, concentration of O2 0.125 and SO3 0.25. Substitute these values in that equation, we get 0.25 here, 0.25 upon 2 raised to 2 into 0.125 upon 2 whole upon 0.25 upon 2 whole raised to 2. Right? We substitute these values, right? Then simple mathematics. 0.25 upon 2 whole raised to 2, 0.25 upon 2 whole raised to 2 get cancelled. They get cancelled. And simple divide by 2 to 0.125. Therefore, answer is O2 divided by 2. Answer is point. If we shift the point here, it is equal to 12.5 into 10 raised to minus 2 divided by 2. Then 6 2s are 12. Then 0.4 multiplied by 0.2 minus 2, it is equal to 0.064. This is your final answer. And therefore, Kc equal to 0.064. This is your final answer. Simple mathematics, right? Any doubt about this numerical? I will repeat the same. We applied law of mass action to this equation, then we get this equation. Then we have the values of these concentrations. We substitute these values. Right? 0.25 divided by 2 get cancelled. Left only this data. We divide this. Answer becomes 0.064. Right? This is the second numerical. Then we are going to start a numerical number 3. Numerical number 3. At 500 Kelvin in 10 dm cube, at 500 Kelvin in a 10 dm cube, comma 12 moles of N2 12 moles of N2 combines with 15 moles of H2 at equilibrium 6 moles of NH3 are formed. Calculate equilibrium constant. Calculate equilibrium constant for the given reaction. At the given temperature. Interesting numerical. At 500 Kelvin in a 10 dm cube, 12 moles of N2 combined with 15 moles of H2. 12 moles of N2 combined with 15 moles of H2. Then at equilibrium 6 moles of ammonia are formed. And our aim is to calculate the equilibrium constant. Yes. Now concentrate whereas on this numerical. Interesting numerical. For the given information we can write reaction N2 plus thrice H2 gives twice NH3. Reaction. 3 points. Initial moles. How many moles of N2 at 10 dm cube? 12 moles. How many moles of H2? 15 moles. Product, no product is found, 0. Second point, moles at equilibrium. Directly, moles of ammonia at equilibrium are given 6. And from 6, our aim is to calculate these two. How many moles left? Right? Now, 1 mole corresponds to 2. Therefore, for 6 moles, how many? 6 divided by 2, 3. Means 3 moles of N2 get reacted. And out of 12, 3 moles get reacted. How many moles left? 9. Therefore, 9 moles. Similarly, we can write whenever the 6 moles, whenever the 3 moles of H2 get react, 2 moles of NH3. Means 3 corresponds to 2. Therefore, 6 corresponds to question mark. 6 into 3 divided by 2. 2 3s are 6. 3 into 3, 9 moles get react. Means out of 15 and 9 moles get react. Then left mole how many? 15 minus 9 means 6 moles get left. 6 moles get left. These are the moles at equilibrium. Then point number 3. concentration at equilibrium in moles per dm cube. Dm cube is 10. 9 divided by 10, 6 divided by 10, 6 divided by 10. These are the concentrations at equilibrium. Then apply the law of mass action to this chemical reaction. We get Kc equal to active mass of NH3 raised to 2 upon active mass of N2 into active mass of H2 raised to 3. After applying law of mass action, we get that equation. We have the values of concentrations. Concentration of NH3, 6 divided by 10. 6 divided by 10 whole raised to 2 whole upon. What is the concentration of N2? 9 divided by 10. What is the concentration of H2? 6 divided by 10 whole raised to 3. Simple mathematics now. 6 divided by 10 raised to 2, 6 divided by 10 raised to 2 get cancelled, 1 left. And therefore we will write 1 upon 9 by 10 left 1, 6 divided by 10. This is exactly equal to 10 into 10, 100 becomes in a numerator 100. 9 into 6 divided by 9 into 6 means 54. 100 divided by 54, and therefore by calculating it is equal to 1.1 then 85, 1.85. This is your final answer. Equilibrium constant equal to 1.85. I hope, right? I will be the same. Initial moles 12, 15, 0. Moles at equilibrium of ammonia are given 6, and from 6 we can calculate these 9 and 6. Concentration at equilibrium in moles per dm cube. Volume is given 10, 9 by 10, 6 by 10, 6 by 10. These are the concentration of these species. We applied a law of mass action and we get Kc equal to active mass of NH3 raised to 2, active mass of N2, active mass of H2 raised to 3. We have the values of these concentrations. By putting the values of concentration, we get this. 6 divided by 10 raised to 2, 6 divided by 10, 3 raised to 2 get cancelled, left 1, then we return left 1. 1 upon 9 by 10 into 6 by 10. 10 into 10, 100. 100 becomes in numerator. 100 divided by 54, it becomes 1.85. Therefore, answer is Kc equal to equilibrium constant for this reaction equal to 1.85. I hope you are getting me. Yes, we'll stop here.